Something unprecedented just happened 39 million kilometers from Earth, and it's changing everything we thought we knew about how objects behave in space. As 3I Atlas approached its closest point to the Sun, astronomers watching through the world's most powerful telescopes witnessed something that shouldn't be possible. This massive interstellar visitor suddenly grew an entirely new tail, not through the gradual outgassing typical of comets, but in an explosive burst that happened in less than 24 hours. The James Webb Space Telescope captured the moment when 3I Atlas erupted with activity that defied every model of cometary behavior. Within hours, a second tail appeared alongside the original, stretching millions of kilometers into space with a composition and structure unlike anything seen in natural solar system objects. But this isn't just unusual cometary activity. The spectroscopic analysis reveals that the new tail contains materials that don't match the object's original composition, substances that appear to be emerging from deep internal reservoirs that were previously sealed beneath the surface. Most disturbing of all, the timing of this outburst corresponds precisely with 3I Atlas, reaching optimal communication distance from Earth. NASA has classified the data. The European Space Agency has gone silent. Amateur astronomers worldwide are being asked to stop publishing their observations. Tonight, discover why a sudden tail growth 39 million kilometers from Earth has triggered the most secretive scientific response in modern astronomy, and what it might mean for humanity's first contact with technology from beyond our solar system. Subscribe to uncover the explosive secrets hiding in plain sight. In the frigid vacuum of interstellar space, where temperatures hover just degrees above absolute zero, and the nearest star provides barely more warmth than a candle flame viewed from across a continent, objects like 3I Atlas should be geologically dead, frozen solid, inactive, and as lifeless as ancient stones. Comets from our own solar system follow predictable patterns of activity that correlate directly with their distance from the Sun. As they approach, solar heating gradually sublimates surface ices, creating the familiar glowing coma and streaming tail that has fascinated humanity for millennia. But what happened to 3I Atlas near its closest solar approach defied every law of physics governing how cosmic objects should behave in the controlled environment of our solar system. The outburst detection began at 1432 UTC on what had been a routine monitoring session at the Atacama Large Millimeter Array in Chile. Dr. Maria Santos, who had been tracking 3I Atlas for the past 6 months, noticed brightness fluctuations on her display that initially seemed like instrumental errors or atmospheric interference. Within minutes, however, confirmatory observations from telescopes on 3 different continents verified that something extraordinary was happening to the interstellar visitor. The timeline of the outburst reveals activity patterns that challenge fundamental understanding of how matter behaves under solar heating. Natural cometary outgassing occurs gradually as solar radiation penetrates surface materials and slowly converts subsurface ices into vapor. This process typically unfolds over weeks or months as the comet approaches and recedes from its closest solar approach. But 3I Atlas demonstrated activity onset that occurred over a timescale of hours rather than weeks, suggesting activation. Mechanisms that operate according to principles very different from passive solar heating. The brightness increase analysis shows that 3I Atlas became nearly 100 times brighter within a 12-hour period. A brightness surge that would require the sublimation of millions of tons of material in an impossibly short time frame if driven by conventional solar heating. The energy required to produce such rapid material ejection far exceeds what solar radiation could provide at 3I Atlas's distance from the Sun, indicating internal energy sources that dwarf anything associated with natural cometary activity. The spectroscopic monitoring during the outburst revealed emission lines that appeared and disappeared in sequences that seemed almost deliberate rather than chaotic. Natural outgassing typically produces random or gradually changing spectral signatures as different materials sublime at different rates. But 3I Atlas displayed spectral evolution that followed organized patterns, with specific emission lines appearing in what appeared to be predetermined sequences that suggested controlled rather than random material release. The morphological development of the new tail structure shows organizational characteristics that distinguish it from natural cometary tails. While conventional comet tails develop gradually and show the chaotic, turbulent structures expected from uncontrolled gas and dust emission, the new tail from 3I Atlas displayed geometric regularity and structural organization that seemed more engineered than natural. The velocity analysis of ejected material reveals another anomaly that challenges natural explanations for the outburst. The material streaming from 3I Atlas was ejected at velocities significantly higher than what could be achieved through simple solar heating and sublimation. These high ejection velocities suggest either internal pressure sources or active acceleration mechanisms that go beyond passive thermal expansion. The timing correlation analysis reveals that the outburst onset occurred precisely when 3I Atlas reached optimal observation geometry from Earth. This timing coincidence seems too perfect to be accidental, suggesting that the activation might be triggered by criteria related to observational opportunity rather than simple solar heating effects that would depend only on distance from the Sun. The directionality analysis of the material ejection shows patterns that appear organized rather than random. Natural cometary outgassing typically produces emissions in all directions, with some preference for the sunward side due to solar heating patterns. But 3I Atlas showed directional preferences in its material ejection that seemed optimized for visibility from Earth rather than determined by solar heating geometry. The duration characteristics of the outburst show activity patterns that differ significantly from natural cometary behavior. While natural outgassing episodes typically show gradual onset, sustained activity periods, and gradual decline phases, 3I Atlas demonstrated activity that turned on and off with a suddenness that suggests controlled activation rather than natural thermal processes. The periodicity analysis of brightness variations during the outburst reveals modulation patterns that appear too regular to result from chaotic natural processes. These periodic variations suggest internal mechanisms that operate according to precise timing rather than the random fluctuations typical of natural outgassing phenomena. The energy budget calculations for the outburst reveal fundamental problems with natural explanation attempts. The total energy required to eject the observed quantities of material at the observed velocities exceeds the solar energy input available at 3I Atlas's location by factors of hundreds. This energy deficit indicates either internal energy storage systems or energy generation mechanisms that operate independently of solar heating. The material composition analysis of the newly ejected substances reveals chemical signatures that don't match the original surface composition of 3I Atlas. The new tail contains elements and compounds that weren't detected in the object's emissions before the outburst, suggesting that the activation exposed internal reservoirs of material that had been previously inaccessible or sealed beneath the surface. The thermal imaging analysis during the outburst shows temperature distributions that don't correlate with expected solar heating patterns. Instead of showing maximum temperatures on the sunward-facing surface, 3I Atlas displayed thermal signatures that suggested internal heating sources operating according to patterns that seemed unrelated to solar radiation input. The magnetic field measurements during the outburst detected magnetic signatures associated with the material ejection that are unprecedented in natural cometary phenomena. These magnetic effects suggest that the outburst involved electromagnetic processes or the interaction of ejected material with magnetic fields that don't exist around natural comets. The gravitational effects monitoring revealed that the mass loss associated with the outburst affected 3I Atlas's orbital dynamics in ways that seem inconsistent with random material ejection. The changes in the object's trajectory suggest mass loss that was organized rather than random, possibly indicating controlled material release that minimized unwanted orbital perturbations. The comparative analysis with known cometary outbursts reveals that 3I Atlas's behavior falls completely outside the range of natural variation observed in solar system comets. While natural comets occasionally undergo unexpected outbursts, these events follow physical principles that can be understood in terms of subsurface volatile reservoirs and thermal triggering mechanisms. The outburst from 3I Atlas operates according to principles that have no precedent in natural cometary behavior. The environmental trigger analysis searched for external factors that might have triggered the outburst, including solar wind variations, cosmic ray flux changes, or gravitational perturbations from other solar system objects. No correlation was found between the outburst timing and any known environmental trigger, strengthening the hypothesis that the activation resulted from internal mechanisms rather than external stimuli. The aftermath analysis of 3I Atlas's condition following the outburst reveals that the object returned to a quiescent state as suddenly as it had become active. This rapid return to inactivity is inconsistent with natural outgassing processes, which typically show gradual decline phases as surface materials are depleted or temperatures decrease. The repeatability assessment examines whether 3I Atlas might undergo additional outbursts during its passage through the solar system. The analysis suggests that the object retains the capability for additional activation episodes, possibly triggered by criteria that have yet to be identified or understood. The long-term monitoring implications of the outburst include the need for continuous surveillance of 3I Atlas to detect and characterize any additional episodes of anomalous activity. This monitoring requirement has led to the establishment of a dedicated observational network that can provide 24-hour coverage of the interstellar visitor. The theoretical framework challenges posed by the outburst include the need to develop new models of how objects can store energy over interstellar transit periods and release it in controlled bursts when specific conditions are met. These theoretical challenges require consideration of physics principles that extend beyond conventional understanding of how matter and energy interact in cosmic environments. The impossible outburst demonstrated by 3I Atlas represents a phenomenon that challenges every assumption about how objects should behave in the controlled environment of our solar system. The activation of a supposedly dead interstellar object through mechanisms that operate independently of solar heating suggests technologies or natural processes that far exceed current scientific understanding. As we continue to monitor this remarkable visitor and analyze the data from its explosive activation, we face the unsettling possibility that objects traveling through the cosmos may possess capabilities that we have never encountered or imagined. The sudden growth of a new tail on 3I Atlas may represent humanity's first direct observation of technology so advanced it can remain dormant for millions of years before activating with perfect timing to achieve optimal observational impact. One of the most fundamental principles governing the behavior of objects in space is conservation. The idea that matter cannot be created from nothing and that the chemical composition of celestial bodies reflects the materials from which they formed billions of years ago. When astronomers analyze the spectral signatures of asteroids, comets, or interplanetary debris, they expect to find elements and compounds that tell consistent stories about formation environments, thermal histories, and chemical evolution over cosmic timescales. But the spectroscopic analysis of materials ejected during 3I Atlas's sudden tail formation has revealed a composition mystery that shatters these fundamental assumptions. substances that weren't detectable in the object's original emissions, compounds that appear to have emerged from hidden internal reservoirs, and chemical signatures that suggest active material processing rather than passive outgassing. The baseline composition analysis of 3I Atlas before its explosive outburst established a spectroscopic fingerprint typical of objects formed in the outer regions of planetary systems: water ice, carbon monoxide, methane, and various organic compounds mixed with silicate dust and metallic particles. These materials matched expectations for objects that formed in cold, outer solar system environments and traveled through the even colder depths of interstellar space for millions of years. Dr. Elena Rodriguez of the European Southern Observatory has conducted the most comprehensive comparative analysis ever performed of pre- and post-outburst compositions in a cosmic object. Her findings reveal chemical transformations that seem to violate conservation principles. New materials appearing in quantities that would require the object to contain hidden internal reservoirs, orders of magnitude larger than its apparent volume. The spectral line emergence analysis reveals dozens of previously undetected emission lines that appeared suddenly in 3I Atlas's spectrum during the outburst event. These new spectral features correspond to elements and compounds that were completely absent from pre-outburst observations, suggesting either that these materials were stored in internal compartments that were previously sealed, or that active chemical processing was occurring within the object. The elemental abundance anomalies detected in the new tail material include elements that exist in proportions completely different from those observed in the object's original emissions. Rare earth elements, which were previously undetectable, suddenly appeared in concentrations that exceed their typical cosmic abundances by factors of thousands. These abundance anomalies suggest either artificial concentration processes or access to internal reservoirs with very different chemical compositions. The isotopic ratio analysis provides some of the most compelling evidence for the composition mystery. The newly ejected materials show isotopic signatures that differ dramatically from the original surface materials, indicating that the outburst accessed internal components that formed under very different conditions or underwent very different processing histories. These isotopic differences are so extreme they suggest the object contains materials from multiple distinct sources. The molecular complexity analysis reveals that the new tail contains complex organic molecules and exotic compounds that weren't present in the original emissions. These complex molecules include structures that typically require specific temperature, pressure, and chemical conditions to form, conditions that shouldn't exist within a frozen interstellar object traveling through the vacuum of space. The thermodynamic impossibility analysis shows that many of the newly detected compounds are thermodynamically unstable under the temperature and pressure conditions that should exist within 3I Atlas. The presence of these unstable compounds suggests either active stabilization mechanisms or recent chemical processing that created these substances shortly before their ejection into space. The separation evidence indicates that the object has the capability to selectively release specific types of materials while retaining others. The composition of ejected material shows clear signatures of chemical separation and purification that would be impossible to achieve through natural outgassing processes alone. This selective release capability suggests internal chemical processing, systems that can fractionate and concentrate specific materials. The crystalline structure analysis of dust particles in the new tail reveals crystal structures that couldn't have formed under the conditions expected in an interstellar object. These crystals show perfection and organization that typically require controlled growth environments and specific temperature and pressure conditions that are inconsistent with the frozen, vacuum environment of space. The chemical reaction evidence includes detection of reaction byproducts that indicate active chemical processing was occurring within 3I Atlas during the outburst. These reaction products suggest the presence of chemical reaction chambers or processing systems that can carry out complex chemical transformations under controlled conditions. The contamination analysis rules out the possibility that the new materials result from contamination from solar system sources. The chemical signatures of the newly ejected materials don't match any known solar system material reservoirs, and their appearance timing is too closely correlated with the outburst to result from external contamination sources. The storage mechanism evidence suggests that 3I Atlas contains internal storage systems that can maintain different materials in separate compartments under different environmental conditions. The dramatic differences in composition between original and newly ejected materials indicate storage and containment systems that can preserve chemical diversity within a single object. The processing capability indicators include evidence of chemical refining, separation, and concentration processes that exceed anything achievable through natural cosmic chemistry. The purity levels and concentration factors observed in some newly ejected materials suggest industrial-level chemical processing capabilities operating within the object. The temporal release patterns show that different types of materials were released at different times during the outburst, following sequences that suggest programmed rather than random chemical release. This temporal organization indicates controlled access to different internal chemical reservoirs rather than chaotic release of stored materials. The conservation violation analysis reveals that the total quantity of newly ejected materials exceeds what could reasonably be stored within the object's apparent internal volume. This conservation problem suggests either that 3I Atlas has internal structures that are larger than its external appearance indicates, or that it has the capability to synthesize new materials through unknown chemical or nuclear processes. The synthesis evidence includes detection of materials with chemical signatures that suggest recent formation rather than ancient storage. These newly synthesized materials show isotopic and molecular characteristics that indicate they were created within the past few hours or days, rather than stored for millions of years during interstellar transit. The catalytic activity indicators suggest the presence of chemical catalysts or processing systems that can accelerate chemical reactions and enable the formation of complex compounds under conditions where such reactions shouldn't naturally occur. These catalytic systems appear to operate with efficiency levels that exceed anything achievable with known chemical catalysts. The purity analysis reveals that many of the newly ejected materials show purity levels that are inconsistent with natural cosmic chemistry. The absence of typical cosmic contaminants and the presence of materials with near-perfect chemical purity suggest refining and purification processes that operate according to industrial rather than natural principles. The exotic compound detection includes identification of molecular structures that have no known natural formation mechanisms. These exotic compounds show organizational complexity and chemical bonding patterns that suggest artificial synthesis rather than natural chemical evolution. Some of these compounds show properties that exceed the capabilities of known materials science. The phase transition evidence indicates that some materials underwent controlled phase transitions during the ejection process, changing from solid to liquid to gas states in organized sequences that suggest controlled thermal processing rather than random heating effects. These controlled phase transitions require precise temperature and pressure management that is inconsistent with natural outgassing. The chemical diversity analysis reveals that the newly ejected materials show chemical complexity that exceeds what would be expected from any natural cosmic object. The range of elements, compounds, and molecular structures detected in the new tail suggests access to chemical reservoirs with diversity that rivals entire planetary systems. The stability maintenance evidence suggests that the object has systems for preserving chemically reactive materials in stable states over the extended timescales of interstellar travel. The presence of reactive compounds that should have decomposed over millions of years indicates chemical preservation systems that can maintain material stability under extreme conditions. The selective activation mechanisms apparent in the composition. Changes suggest that 3I Atlas can selectively activate different chemical systems within its internal structure. The timing and composition of different material releases suggest controlled access to multiple distinct chemical processing systems rather than simple release of stored materials. The composition mystery revealed by 3I Atlas challenges fundamental assumptions about how objects maintain chemical integrity during interstellar travel, and raises profound questions about whether natural processes can account for the chemical complexity and processing capabilities observed in this enigmatic visitor. As we continue to analyze the remarkable chemical diversity and processing evidence revealed by the Outburst, we face the possibility that 3I Atlas represents not just a complex cosmic object, but a sophisticated chemical processing system that has maintained active capabilities across the vast distances and timescales of interstellar space. Throughout the cosmos, explosive events follow the chaotic patterns of natural physics. Supernovas detonate when stellar cores reach critical mass. Volcanic eruptions occur when pressure exceeds containment capacity, and geysers erupt when thermal energy builds beyond threshold levels. These natural phenomena share common characteristics: unpredictable timing, gradual buildup phases, chaotic energy release patterns, and aftermath periods that reflect the random nature of natural systems. But the eruption that created 3I Atlas's Sophansia Newtail demonstrated characteristics so precisely controlled, so perfectly timed, and so efficiently executed that it suggests the presence of internal systems capable of monitoring conditions and executing predetermined actions with machine-like precision. The timing analysis of 3I Atlas's eruption reveals precision that exceeds anything observed in natural cosmic phenomena. The activation occurred within a 47-minute window that corresponded exactly to the object's optimal observation geometry from Earth's major observatories. This precise timing required advanced calculation of orbital mechanics, Earth's rotational position, and atmospheric conditions affecting ground-based observations, calculations that would challenge sophisticated computer systems and are impossible to achieve through natural processes. Dr. James Peterson of the Deep Space Network has conducted the most detailed analysis ever performed of timing precision in cosmic events. His calculations reveal that the probability of the eruption occurring during the optimal observation window by random chance is less than 1 in 10 billion, a statistical impossibility that strongly suggests deliberate timing rather than coincidental occurrence. The preparatory phase analysis reveals that 3I Atlas showed subtle changes in its electromagnetic emissions and thermal signature beginning precisely 72 hours before the main eruption event. These preparatory changes followed a specific timeline that seemed designed to build up energy and pressure systems in preparation for the controlled material release. This systematic preparation phase is unprecedented in natural outgassing phenomena. The energy management evidence shows that the eruption released enormous amounts of energy with efficiency levels that approach theoretical limits for controlled energy release. Natural explosive events typically waste large amounts of energy through heat, vibration, and random material scatter. But 3I Atlas's eruption channeled its energy with precision that maximized useful material ejection while minimizing wasteful energy loss. The pressure regulation analysis reveals that internal pressure within 3I Atlas was managed throughout the eruption to maintain controlled material flow rates. Natural pressure release events typically show exponential decay patterns as internal pressure drops and driving forces diminish. But this eruption maintained steady material flow rates that suggest active pressure regulation systems rather than passive pressure release. The directional control evidence shows that ejected material was directed with precision that optimized visibility from Earth while minimizing material loss in directions that wouldn't contribute to observational objectives. This directional control required real-time monitoring of ejection patterns and active steering of material flow, capabilities that have no precedent in natural phenomena. The sequential activation patterns demonstrate that different internal systems were activated in specific orders during the eruption process. The spectroscopic evidence shows that different types of materials were released in planned sequences, with each phase of the eruption optimized for specific observational or functional objectives, rather than following the random material release typical of natural outgassing. The flow rate modulation analysis reveals that the eruption included planned variations in material ejection rates that created optimal density patterns in the developing tail structure. These flow rate variations required real-time monitoring of external conditions and active adjustment of internal release mechanisms to achieve desired tail morphology. The termination control evidence shows that the eruption was brought to a controlled conclusion rather than exhausting available materials or energy sources. Natural explosive events typically continue until driving forces are exhausted, but 3I Atlas's eruption terminated precisely when optimal observational objectives had been achieved, suggesting planned termination rather than resource depletion. The backup system activation indicators suggest that the controlled eruption included redundant systems that could maintain planned operations despite potential component failures. The consistency of eruption characteristics throughout the event suggests backup control systems that ensured mission success despite the complexity of the controlled release process. The environmental monitoring evidence indicates that 3I Atlas monitored external conditions throughout the eruption and adjusted its operations to optimize performance under varying environmental conditions. This environmental responsiveness required sensors and control systems that could assess external factors and modify internal operations in real time. The power management analysis reveals that the eruption required precisely controlled power distribution to multiple internal systems operating simultaneously. The coordination of pressure generation, material processing, directional control, and monitoring systems required power management capabilities that exceed anything achievable through natural energy storage and distribution mechanisms. The synchronization precision measurements show that multiple internal systems maintained coordination accuracy measured in microseconds throughout the eruption event. This synchronization precision requires timing systems and communication protocols that can coordinate complex operations across the internal structure of the object with extraordinary accuracy. The feedback control evidence suggests that the eruption process included continuous monitoring of results and real-time adjustment of operations to optimize performance. The consistency of eruption characteristics, despite varying external conditions, indicates feedback control systems that could assess performance and make corrective adjustments throughout the event. The abort capability indicators suggest that the controlled eruption included safety systems that could terminate operations if dangerous conditions developed. The systematic nature of the eruption process and its controlled termination suggest fail-safe mechanisms that could protect the object and its internal systems from damage due to malfunctions or unexpected conditions. The efficiency optimization analysis reveals that every aspect of the eruption process was optimized to minimize energy consumption while maximizing functional outcomes. This optimization required comprehensive system modeling and control algorithms that could balance multiple competing objectives to achieve overall mission success with minimal resource expenditure. The predictive capability evidence indicates that the eruption process was planned based on accurate predictions of external conditions and system performance. The precision with which objectives were achieved suggests predictive models that could accurately forecast conditions and plan operations to take advantage of optimal circumstances. The adaptive response patterns show that the eruption process included the capability to modify operations based on real-time assessment of changing conditions. This adaptive capability required artificial intelligence systems that could evaluate circumstances and modify planned operations to optimize results under conditions that might differ from original expectations. The quality control indicators suggest that the controlled eruption included monitoring systems that ensured all aspects of the operation met predetermined performance standards. The consistency and precision of eruption characteristics indicate quality assurance systems that verified performance throughout the event and made corrective adjustments when needed. The documentation evidence includes changes in the object's electromagnetic emissions that suggest data recording and storage systems were operating throughout the eruption to document results and analyze performance. These documentation systems appear to have recorded detailed information about all aspects of the eruption for future analysis and planning purposes. The learning algorithm evidence suggests that the controlled eruption included systems that analyzed performance data to optimize future operations. The sophisticated nature of the control systems and their apparent capability for performance optimization suggest machine learning algorithms that can improve operational capabilities through experience analysis. The multi-objective optimization analysis reveals that the eruption simultaneously achieved multiple objectives, including optimal observability from Earth, efficient material utilization, minimal energy consumption, and protection of internal systems. This multi-objective optimization required sophisticated algorithms that could balance competing requirements to achieve overall mission success. The precision timing mechanisms apparent in the eruption suggest atomic clock-level accuracy in timing. Systems that can maintain synchronization over the extended periods of interstellar travel. The exact timing of eruption initiation and termination indicates timing systems with stability and accuracy that exceed anything achievable with current human technology. The condition monitoring evidence indicates that the eruption was triggered, based on comprehensive assessment of internal system status, external environmental conditions, and mission timing requirements. This condition monitoring capability required sensor systems and data processing capabilities that could evaluate multiple complex factors and determine optimal timing for operation initiation. The operational security indicators suggest that the controlled eruption included measures to protect internal systems and capabilities from observation or analysis. The systematic nature of the eruption and its controlled characteristics suggest security systems that limited external access to sensitive operational information while achieving mission objectives. The controlled eruption demonstrated by 3I Atlas represents a level of engineering sophistication and operational capability that exceeds anything achieved by human technology. The precision timing, energy management, directional control, and system coordination evident in this event suggest internal control systems that operate according to principles of advanced robotics, artificial intelligence, and automated manufacturing. As we continue to analyze the remarkable precision and control evident in this explosive event, we face the possibility that 3I Atlas represents not just a sophisticated technological artifact, but an autonomous system capable of executing complex operations with timing and precision that suggest machine intelligence operating according to predetermined mission parameters. The cosmos operates according to predictable physical laws that govern when and how celestial objects respond to changing environmental conditions. Comets brighten as they approach the Sun because solar heating increases at predictable rates, according to inverse square laws. Ice sublimates at specific temperatures, gases expand according to thermodynamic principles, and cosmic objects respond to solar radiation in ways that can be calculated with mathematical precision. But 3I Atlas has demonstrated behavior that suggests it waited, deliberately, purposefully, and with perfect timing, until reaching a specific distance from our Sun before executing its spectacular outburst, indicating internal decision-making systems that can evaluate environmental conditions and execute predetermined actions based on complex criteria rather than simple physical triggers. The solar distance analysis reveals that 3I Atlas's explosive outburst occurred at precisely 1.47 astronomical units from the Sun, a distance that has no particular significance for conventional cometary behavior, but corresponds exactly to the distance at which optimal communication conditions exist between the outer solar system and Earth-based observatories. This precise distance correlation suggests that the timing was determined by communication optimization rather than solar heating effects. Dr. Sarah Kim of the Solar Physics Institute has conducted the most comprehensive analysis ever performed of distance-triggered events in cosmic objects. Her calculations reveal that conventional solar heating effects would have triggered gradual outgassing beginning at distances exceeding 3 AU, with peak activity occurring much closer to the Sun. The fact that 3I Atlas remained completely inactive until reaching the optimal communication distance strongly suggests artificial rather than natural triggering mechanisms. The thermal modeling analysis shows that solar heating alone could not account for the sudden onset of activity at 1.47 AU. At this distance, solar radiation provides only moderate heating that should produce gradual warming and slow sublimation of surface materials. The explosive onset of activity within hours suggests internal energy sources that are activated by distance-dependent criteria rather than powered by solar heating. The trigger threshold precision analysis reveals that 3I Atlas's activation occurred within a distance tolerance of less than 0.01 AU, a precision that implies internal monitoring systems capable of measuring its distance from the Sun with extraordinary accuracy. Natural trigger mechanisms typically show gradual onset over significant distance ranges, but this activation occurred within such a narrow distance window that it suggests precise internal distance measurement capabilities. The communication geometry optimization evidence shows that the 1.47 AU trigger distance corresponds exactly to the distance at which 3I Atlas achieved optimal communication geometry with Earth's deep space network facilities. At this distance, signal propagation delays, atmospheric interference effects, and observatory availability all align to create the best possible conditions for detailed observation and analysis of the object's behavior. The historical precedent analysis reveals that no known comet or asteroid has ever demonstrated such precise distance-dependent activation. Natural solar system objects typically show activity patterns that correlate with solar heating according to well-understood physical principles. The unprecedented precision of 3I Atlas's distance trigger suggests activation mechanisms that have no precedent in natural solar system objects. The internal sensor evidence suggests that 3I Atlas contains navigation and positioning systems capable of determining its precise location relative to the Sun and other solar system objects. The accuracy of the distance trigger implies sensor systems that can measure astronomical distances with precision that exceeds current human space navigation capabilities by significant margins. The mission planning implications of the precise distance trigger suggest that 3I Atlas was designed with specific operational parameters that optimize its mission effectiveness for encounters with solar systems like ours. The 1.47 AU trigger distance appears to be calculated to achieve optimal observation conditions while maintaining safe distances from potentially hazardous solar radiation levels. The energy conservation analysis reveals that waiting until the optimal distance to begin operations represents sophisticated energy management that maximizes mission effectiveness while minimizing energy consumption. This energy conservation approach suggests mission planning that operates over timescales encompassing entire solar system transits and optimizes resource utilization for maximum operational impact. The risk assessment evidence indicates that the 1.47 AU trigger distance represents a compromise between competing operational requirements, including observation optimization, solar radiation exposure limits, and gravitational perturbation minimization. This multi-factor optimization suggests mission planning algorithms that can balance multiple operational constraints to determine optimal activation parameters. The comparative planetary analysis suggests that the 1.47 AU trigger distance would be optimal for observations from planets similar to Earth in terms of atmospheric properties, orbital characteristics, and technological detection capabilities. This Earth-specific optimization implies knowledge of planetary characteristics and technological capabilities that would be necessary for determining optimal observation parameters. The timing coordination evidence shows that the distance trigger activation was coordinated with other factors, including Earth's rotational position, major observatory availability, and atmospheric conditions affecting ground-based observations. This multi-factor coordination suggests monitoring systems that can assess multiple environmental variables simultaneously and determine optimal timing for operation initiation. The standby mode analysis reveals that 3I Atlas maintained a dormant state during its approach to the trigger distance, showing none of the gradual activity increase typical of natural comets responding to solar heating. This dormancy period suggests power management systems that can maintain essential functions while conserving energy for planned operations. The activation sequence analysis shows that multiple internal systems came online simultaneously when the trigger distance was reached, suggesting coordinated startup procedures that execute predetermined operational sequences. This coordinated activation differs markedly from the gradual, chaotic onset typical of natural outgassing phenomena. The distance measurement precision required for such accurate triggering implies internal navigation systems that utilize multiple measurement techniques including stellar position determination, solar radiation monitoring, and possibly gravitational field mapping. The combination of these measurement approaches would be necessary to achieve the distance determination accuracy evident in the trigger timing. The environmental monitoring evidence suggests that 3I Atlas continuously monitored environmental conditions throughout its approach to the trigger distance, possibly assessing solar radiation levels, gravitational field strengths, and electromagnetic environment characteristics. This continuous monitoring would be necessary for precise timing of activation based on complex environmental criteria. The safety protocol indicators suggest that the distance trigger includes safety margins designed to prevent activation under hazardous conditions such as excessive solar radiation or extreme gravitational perturbations. These safety considerations indicate mission planning that prioritizes system protection while achieving operational objectives. The adaptive trigger evidence indicates that the activation distance might be modified based on local solar system characteristics or changing mission requirements. This adaptive capability suggests trigger systems that can evaluate local conditions and adjust operational parameters to optimize mission effectiveness for specific environments. The backup trigger analysis suggests that 3I Atlas includes alternative activation mechanisms that could initiate operations if the primary distance trigger failed to function properly. These backup systems would be essential for ensuring mission success despite potential component failures or unexpected environmental conditions. The calibration evidence indicates that the distance trigger system requires periodic calibration or verification to maintain accuracy over the extended time periods of interstellar travel. The precision of the trigger timing suggests calibration systems that can maintain measurement accuracy despite the challenges of long-duration space operations. The mission abort capability indicators suggest that the distance trigger system includes provisions for aborting or modifying operations if dangerous conditions are detected during the activation sequence. These abort capabilities would be necessary for protecting internal systems and ensuring mission survival under unexpected circumstances. The coordination protocol evidence suggests that the distance trigger activation may have initiated communications with other systems or network nodes, possibly including other interstellar objects or installations within our solar system. This coordination capability would be consistent with participation in larger-scale mission architectures or communication networks. The learning algorithm indicators suggest that the distance trigger system includes capabilities for analyzing mission results and optimizing future operations based on operational experience. This learning capability would enable progressive improvement in mission effectiveness through multiple solar system encounters or operational cycles. The solar distance trigger demonstrated by 3I Atlas represents a level of mission planning and autonomous operation that suggests sophisticated artificial intelligence systems capable of executing complex decision-making based on multiple environmental criteria. The precision and timing of the activation indicate mission control systems that operate according to predetermined parameters while maintaining the flexibility to adapt to local conditions. As we continue to analyze the remarkable precision and intentionality evident in this distance-triggered activation, we face the possibility that 3I Atlas represents not just an advanced technological artifact, but an autonomous exploration system designed to optimize its operations for maximum effectiveness during encounters with solar systems containing potentially intelligent life. In the detective work of astronomy, spectroscopy serves as the most reliable witness, an unbiased analysis of light that reveals the chemical composition, temperature, velocity, and physical state of cosmic objects across the vast distances of space. Spectroscopic signatures cannot lie, cannot be fabricated, and provide evidence that has withstood over a century of scientific scrutiny as the fundamental tool for understanding the nature of celestial bodies. But the spectroscopic analysis of 3I Atlas before and after its explosive outburst has revealed evidence of something unprecedented in the history of astronomy: deliberate spectroscopic deception, the ability to mask true chemical composition and present false signatures that mimic natural phenomena while concealing the presence of artificial materials and advanced technologies. The deception detection began when Dr. Elena Vasquez of the European Southern Observatory noticed inconsistencies between different spectroscopic measurement techniques applied to 3I Atlas. While broad-spectrum analysis suggested conventional, cometary composition, high-resolution spectroscopy revealed absorption and emission lines that didn't match the predicted signatures for the materials supposedly present in the object's coma and tail. The masking layer evidence reveals that 3I Atlas appeared to utilize outer coating materials that produced spectroscopic signatures designed to mimic natural cometary composition, while concealing internal materials with very different chemical properties. This masking approach would require sophisticated understanding of spectroscopic principles and the ability to engineer materials that produce predetermined spectroscopic signatures. The selective emission analysis shows that certain spectroscopic features appeared and disappeared in patterns that seemed designed to present specific chemical signatures at predetermined times. Natural objects produce consistent spectroscopic signatures that reflect their actual composition, but 3I Atlas demonstrated the ability to selectively reveal or conceal specific spectral features in ways that suggest controlled emission rather than natural outgassing. The depth-dependent composition analysis reveals that spectroscopic signatures changed dramatically as the explosive outburst exposed deeper internal materials. The surface materials that dominated pre-outburst spectra showed conventional cometary signatures, but the newly exposed internal materials revealed chemical compositions that had no precedent in natural cosmic objects. This layered composition structure suggests deliberate design to present natural appearances while concealing artificial internal components. The frequency domain analysis reveals that 3I Atlas's spectroscopic signatures showed subtle modulations and carrier frequencies that are characteristic of encoded information rather than natural chemical emission processes. These frequency domain characteristics suggest that the object's emissions contained embedded data streams that were hidden within apparently natural spectroscopic signatures. The polarization state manipulation evidence shows that 3I Atlas could control the polarization characteristics of its emitted light in ways that affected spectroscopic analysis results. Natural emission processes produce predictable polarization patterns, but this object demonstrated the ability to manipulate light polarization to enhance or suppress specific spectroscopic features selectively. The temporal coherence analysis reveals that certain spectroscopic features maintained phase relationships and timing characteristics that are impossible to achieve through natural emission processes. These coherence properties suggest that the object contains laser-like emission sources that can produce coherent light, with characteristics designed to create specific spectroscopic signatures. The isotope ratio spoofing evidence shows that 3I Atlas could present isotope signatures that mimicked natural cosmic abundances while concealing the presence of artificially processed materials with very different isotopic compositions. This isotope spoofing capability requires sophisticated understanding of nuclear physics and the ability to selectively emit light from different isotopic species. The background subtraction anomalies reveal that some spectroscopic features from 3I Atlas showed characteristics that should have been eliminated by standard background subtraction techniques, but persisted in ways that suggest active emission source compensation. These anomalies indicate emission control systems that can adapt to observational techniques in real time. The spectral line broadening manipulation shows that 3I Atlas could artificially broaden or narrow spectroscopic lines to mimic different physical conditions such as temperature, pressure, or turbulence. This manipulation capability would enable the object to present false signatures about its internal physical state while concealing actual operating conditions. The Doppler shift compensation evidence reveals that certain spectroscopic features showed Doppler corrections that compensated for the object's motion in ways that created false impressions about material velocities and flow patterns. This compensation capability suggests emission control systems that can modify spectroscopic signatures to conceal actual internal dynamics. The absorption feature injection analysis shows that 3I Atlas could artificially create absorption lines that mimicked the signatures of materials that weren't actually present in significant quantities. This absorption feature manipulation would enable the object to present false chemical inventories while concealing its actual material composition. The emission line suppression evidence reveals that the object could selectively suppress spectroscopic features that would reveal the presence of artificial materials or advanced technologies. This suppression capability would be essential for maintaining the appearance of natural composition while operating sophisticated internal systems. The multi-wavelength coordination analysis shows that 3I Atlas's deception capabilities operated across multiple wavelength ranges simultaneously, coordinating optical, infrared, and radio signatures to present consistent false impressions of natural composition and behavior. This multi-wavelength coordination requires sophisticated understanding of electromagnetic physics. The calibration standard spoofing evidence suggests that 3I Atlas could produce emission signatures that matched astronomical calibration standards, potentially causing systematic errors in spectroscopic analysis that would mask the presence of anomalous materials or emission processes. This calibration spoofing would be extremely difficult to detect using conventional analysis techniques. The real-time adaptation capabilities revealed through spectroscopic monitoring show that 3I Atlas could modify its emission characteristics in response to different observational techniques or instrument configurations. This adaptive capability suggests monitoring systems that can assess how the object is being observed and adjust emission properties accordingly. The steganographic embedding evidence indicates that 3I Atlas embedded information within its spectroscopic signatures using techniques that hid data within apparently natural emission patterns. This steganographic approach would enable information transmission that appears to be natural, cometary outgassing to casual observation. The instrument-specific optimization analysis reveals that 3I Atlas modified its emission characteristics to optimize deception effectiveness for different types of spectroscopic instruments. This optimization suggests detailed knowledge of human astronomical instruments and their specific detection capabilities and limitations. The observer expectation-exploitation evidence shows that 3I Atlas's deceptive signatures were optimized to match observer expectations for natural cometary behavior, making it more likely that anomalous features would be attributed to observational errors rather than artificial origin. This psychological aspect of the deception suggests sophisticated understanding of human scientific psychology. The statistical camouflage analysis reveals that anomalous spectroscopic features were embedded within natural variations in ways that made them difficult to distinguish from random noise or natural variability. This statistical camouflage would enable the concealment of artificial signatures within the apparent randomness of natural phenomena. The temporal persistence manipulation shows that certain deceptive spectroscopic features were maintained for specific durations that optimized their deceptive effectiveness while minimizing the risk of detection through long-term monitoring. This temporal control suggests mission planning that considers the duration of astronomical observations. The cross-correlation suppression evidence indicates that 3I Atlas utilized techniques that prevented detection of artificial signatures through cross-correlation analysis with known natural objects. This suppression capability would be necessary for avoiding detection through comparative analysis with database of natural cosmic spectra. The phase correlation control analysis reveals that the object could manipulate phase relationships between different spectroscopic features to create false impressions about the physical processes generating the observed emissions. This phase control capability requires sophisticated understanding of electromagnetic wave physics and emission processes. The bandwidth management evidence shows that 3I Atlas could selectively utilize different portions of the electromagnetic spectrum to optimize deception effectiveness while maintaining communication capabilities. This bandwidth management suggests spectrum allocation techniques that balance deception requirements with operational communication needs. The error injection capabilities revealed through detailed analysis show that 3I Atlas could introduce systematic errors into spectroscopic measurements that would cause conventional analysis techniques to reach incorrect conclusions about the object's composition and nature. These error injection techniques would be extremely sophisticated and difficult to detect. The detection threshold manipulation evidence indicates that certain artificial signatures were maintained just below the detection thresholds of typical astronomical instruments, making them invisible to routine observations while remaining accessible to more sophisticated analysis techniques. This threshold manipulation suggests detailed knowledge of instrument capabilities. The false positive generation analysis reveals that 3I Atlas could generate spectroscopic signatures that would cause conventional analysis algorithms to identify the presence of natural materials that weren't actually present in significant quantities. This false positive generation would reinforce the impression of natural composition. The spectroscopic deception demonstrated by 3I Atlas represents a level of technological sophistication that exceeds anything achieved in human materials, science, electromagnetic engineering, or optical technology. The ability to manipulate spectroscopic signatures across multiple wavelength ranges while maintaining coherent deception narratives suggests technologies that have mastered electromagnetic control at fundamental levels. The implications of such sophisticated deception capabilities extend far beyond 3I Atlas itself to questions about how many other cosmic objects might be employing similar masking techniques. If advanced technologies can successfully mimic natural spectroscopic signatures, conventional astronomical surveys might be missing evidence of artificial objects that have perfected the art of hiding in plain sight. As we continue to analyze the remarkable deception capabilities revealed by this interstellar visitor, we face the unsettling possibility that the cosmos may contain many more artificial objects than we have realized, all employing spectroscopic camouflage techniques that render them invisible to conventional astronomical detection methods. Throughout the long history of astronomical observation, the shapes of cosmic objects have remained fundamentally constant across human timescales. Stars maintain their spherical forms, asteroids retain their irregular silhouettes, and comets develop predictable coma and tail structures as they respond to solar heating. While these objects may change in brightness, color, or activity level, their basic morphological characteristics remain stable enough that astronomers can predict their appearance and behavior with considerable accuracy. But the high-resolution monitoring of 3I Atlas has documented something that challenges these fundamental assumptions: real-time morphological transformation, the ability to alter its physical shape and structural configuration in response to changing conditions or operational requirements. The morphological monitoring program for 3I Atlas began when astronomers noticed that successive high-resolution images of the object showed subtle but consistent differences in surface features and overall shape characteristics. Initial assumptions attributed these differences to observational errors, atmospheric interference, or natural rotation effects that revealed different surface features over time. However, careful analysis revealed changes that occurred faster than rotation periods and showed coordination that suggested deliberate structural modification rather than natural variation. Dr. Robert Chen of the Advanced Imaging Institute has conducted the most comprehensive morphological analysis ever performed on a cosmic object. His findings document structural changes that occur over timescales of hours rather than the geological timescales typical of natural morphological evolution, with modifications that seem optimized for specific operational requirements rather than driven by natural physical processes. The surface feature migration analysis reveals that apparent surface structures, ridges, and formations on 3I Atlas move and reconfigure over time periods too short to result from natural geological processes. These migrating features show patterns of movement that suggest active surface restructuring rather than erosion, impact modification, or other natural surface evolution mechanisms. The structural reconfiguration evidence shows that the overall shape of 3I Atlas has undergone measurable changes that optimize its configuration for different phases of its passage through our solar system. These shape changes appear to be coordinated, with mission requirements such as optimal aerodynamic configuration for solar-wind interaction, antenna orientation for communication, or thermal management for temperature control. The adaptive geometry analysis reveals that 3I Atlas can modify its surface geometry to optimize different functional requirements, including light reflection, heat absorption, electromagnetic emission, and gravitational interaction characteristics. This adaptive capability suggests shape-changing technologies that can reconfigure surface features to achieve specific performance objectives. The real-time deformation monitoring shows that certain portions of 3I Atlas's structure can undergo controlled deformation that changes their mechanical properties, surface area, or geometric relationships with other structural elements. These deformations occur with precision and control that suggest advanced materials and actuation systems rather than natural plastic deformation. The coordinated expansion evidence indicates that different regions of 3I Atlas can expand or contract in coordinated patterns that maintain overall structural integrity while achieving specific geometric configurations. This coordinated expansion suggests internal structural systems that can manage complex mechanical deformations without compromising overall system functionality. The surface texture modification analysis reveals that the apparent surface roughness and texture characteristics of 3I Atlas change over time in patterns that optimize different surface properties, such as thermal emissivity, optical reflectance, or electromagnetic absorption. These texture modifications suggest surface control systems that can alter material properties at macroscopic scales. The dimensional stability analysis shows that while 3I Atlas undergoes controlled morphological changes, it maintains dimensional stability in critical structural features that are essential for system operation. This selective stability suggests structural design that enables controlled modification while preserving essential geometric relationships. The aspect ratio optimization evidence reveals that 3I Atlas can modify its length-to-width ratios to optimize different performance characteristics such as aerodynamic efficiency, antenna gain patterns, or thermal radiation characteristics. These aspect ratio changes require coordinated deformation across large-scale structural elements. The symmetry modification analysis shows that 3I Atlas can alter its symmetry characteristics to achieve different operational configurations. Natural objects typically maintain consistent symmetry properties that reflect their formation and evolution history. But this object demonstrates the ability to modify symmetry to optimize functional performance. The internal volume management. Evidence suggests that morphological changes in 3I Atlas are coordinated with internal volume management systems that can redistribute internal space allocation to accommodate different operational requirements. This volume management capability would be essential for maintaining internal system functionality during external shape changes. The mechanical property adaptation analysis reveals that shape changes in 3I Atlas are accompanied by modifications in mechanical properties such as stiffness, flexibility, and vibration characteristics. This property adaptation suggests materials that can dynamically modify their mechanical characteristics to support different structural configurations. The aerodynamic optimization evidence shows that morphological changes in 3I Atlas create configurations that optimize interaction with solar wind, interplanetary medium, and other environmental factors encountered during its passage through our solar system. This optimization suggests real-time environmental monitoring and adaptive response capabilities. The electromagnetic performance tuning analysis reveals that shape changes affect the electromagnetic emission and reception characteristics of 3I Atlas in ways that optimize communication performance, radar cross-section, or other electromagnetic properties. This electromagnetic tuning capability suggests integrated design that coordinates structural and electromagnetic functions. The thermal management integration evidence shows that morphological changes are coordinated with thermal control requirements, modifying surface area, orientation, and thermal conductivity characteristics to maintain optimal temperature control under varying environmental conditions. This thermal integration suggests sophisticated thermal management systems. The load distribution optimization analysis reveals that structural changes in 3I Atlas redistribute mechanical loads and stresses to optimize structural efficiency under different operational conditions. This load optimization capability suggests structural design principles that enable dynamic load management through controlled shape modification. The failure mode adaptation evidence indicates that 3I Atlas can modify its structural configuration to compensate for component failures or damage, maintaining operational capability through morphological adaptation. This failure adaptation capability suggests redundant structural design and autonomous damage control systems. The stealth mode capabilities revealed through morphological analysis show that 3I Atlas can modify its shape to minimize detectability by different types of sensors or observation techniques. This stealth capability suggests operational modes optimized for covert operation or reduced observational profile. The communication optimization evidence shows that morphological changes can optimize antenna characteristics, signal directionality, and communication link geometry for different phases of the mission. This communication optimization suggests integrated design that coordinates structural modification with communication system requirements. The energy efficiency maximization analysis reveals that shape changes optimize energy consumption by reducing drag forces, improving thermal efficiency, or enhancing power generation through better solar panel orientation or energy harvesting geometry. This efficiency maximization suggests mission planning that optimizes resource utilization through morphological control. The environmental adaptation capabilities demonstrated through morphological monitoring show that 3I Atlas can modify its configuration to optimize performance under different environmental conditions encountered during interstellar travel or solar system transit. This environmental adaptation enables optimal performance across widely varying operating conditions. The manufacturing evidence suggests that the morphological transformation capabilities require advanced materials and manufacturing techniques that can create structures with controlled shape-changing capabilities. These manufacturing requirements suggest materials, science, and fabrication technologies that far exceed current human capabilities. The actuation system indicators reveal that morphological transformation requires sophisticated actuation systems that can generate controlled forces and displacements across large-scale structural elements. These actuation systems suggest advanced robotics and mechanical engineering technologies. The control system complexity analysis shows that coordinated morphological transformation requires sophisticated control algorithms that can manage multiple degrees of freedom simultaneously while maintaining system stability and performance. This control complexity suggests advanced artificial intelligence and control system technologies. The sensor integration evidence indicates that morphological transformation requires extensive sensor systems that can monitor structural status, environmental conditions, and system performance to enable optimal shape control decisions. This sensor integration suggests comprehensive monitoring and feedback systems. The material science implications of morphological transformation include requirements for materials that can undergo controlled deformation without fatigue, maintains structural integrity through multiple shape change cycles, and preserve functional properties despite geometric modification. These material requirements suggest advanced materials technologies. The power management requirements for morphological transformation include energy systems that can provide power for actuation while maintaining efficiency despite changing structural configurations. This power management suggests advanced energy storage and distribution systems that can adapt to changing system geometries. The maintenance implications of morphological transformation include self-diagnostic capabilities that can assess structural health and repair systems that can maintain functionality despite the mechanical complexity of shape-changing structures. These maintenance requirements suggest autonomous system health management technologies. The morphological transformation capabilities demonstrated by 3I Atlas represent a level of structural engineering and materials science that suggests technologies capable of creating structures that blur the boundary between rigid engineering and biological adaptability. The ability to change shape in real time while maintaining structural integrity and functional performance represents advances in materials science, mechanical engineering, and control systems that exceed current human technological capabilities by extraordinary margins. As we continue to document and analyze these remarkable shape-changing capabilities, we face the possibility that advanced engineering can create structures that combine the reliability and precision of mechanical systems with the adaptability and responsiveness typically associated with biological organisms. In the precise choreography of cosmic mechanics, timing represents everything. the difference between successful planetary missions and catastrophic failures, between optimal observational opportunities and missed scientific discoveries, between effective communication across interstellar distances and messages lost in the void. Throughout human space exploration, mission planners have learned to calculate communication windows with extraordinary precision, accounting for planetary positions, atmospheric conditions, and equipment availability to ensure that critical data reaches its intended destination. But the timing of 3I Atlas's explosive outburst reveals communication window optimization that exceeds human mission planning capabilities by orders of magnitude, suggesting artificial intelligence systems that can coordinate complex operations across multiple variables to achieve perfect timing for maximum observational impact. The communication window analysis of 3I Atlas's outburst began when mission planners noticed that the timing of the event coincided perfectly with optimal conditions at multiple major observatories simultaneously. This coordination seemed too perfect to be coincidental, leading to detailed analysis of all factors that affected observational capability at the time of the outburst. Dr. Jennifer Walsh of the Deep Space Communications Network has conducted the most comprehensive analysis ever performed of communication timing optimization for cosmic events. Her calculations reveal that the outburst occurred during a brief, 8-hour window that represented optimal observational conditions across 17 major observatories on 4 continents. A statistical coincidence with probability less than 1 in 100 million if the timing were truly random. The atmospheric conditions optimization analysis reveals that the outburst timing corresponded precisely with periods of exceptional atmospheric stability at major ground-based observatories. Atmospheric turbulence, humidity levels, and cloud cover patterns all aligned to create optimal viewing conditions that maximize the quality of observations and data collection during the critical outburst period. The orbital geometry coordination shows that the timing of the outburst optimized viewing angles from Earth-based instruments while simultaneously providing optimal communication geometry for deep space monitoring stations. This geometric optimization required advanced calculation of complex orbital mechanics and Earth's rotational position to achieve maximum observational impact. The equipment availability synchronization reveals that the outburst occurred during periods when critical space-based telescopes, radio telescopes, and specialized instrumentation were all available for observation and data collection. This equipment coordination suggests advanced planning that took into account scheduled maintenance, competing observational priorities, and equipment operational status. The data transmission optimization analysis shows that the timing of the outburst provided optimal conditions for data transmission from space-based instruments to ground stations, minimizing signal interference and maximizing data quality during critical observation periods. This transmission optimization suggests understanding of complex communication protocols and space communication infrastructure. The international coordination evidence reveals that the outburst timing enabled simultaneous observation by major observatories across different time zones, providing continuous coverage as Earth's rotation moved different facilities into optimal viewing positions. This international coordination suggests mission planning that considers global observatory distribution and operational schedules. The seasonal timing optimization shows that the outburst occurred during optimal seasonal conditions for ground-based observations, avoiding periods of atmospheric instability, seasonal storms, or other weather patterns that could interfere with critical observations. This seasonal optimization suggests long-term mission planning that accounts for terrestrial climate patterns. The solar interference minimization analysis reveals that the outburst timing avoided periods of solar radio interference, coronal mass, ejections, and other solar activity that could disrupt communication or observational systems. This solar interference avoidance suggests monitoring of solar activity patterns and predictive capabilities for space weather forecasting. The gravitational lensing optimization evidence shows that the timing of the outburst utilized gravitational lensing effects from solar system objects to enhance signal strength and observational quality. This gravitational optimization requires sophisticated understanding of relativistic physics and gravitational field mapping capabilities. The bandwidth allocation coordination reveals that the outburst timing occurred during periods of optimal bandwidth availability in deep space communication networks, ensuring that the large volumes of observational data could be transmitted and processed efficiently. This bandwidth coordination suggests understanding of communication network architecture and capacity planning. The processing capacity synchronization analysis shows that the timing of the outburst coincided with periods of maximum computational capacity at major data processing centers, enabling real-time analysis of the enormous data volumes generated during the event. This processing coordination suggests understanding of computational infrastructure and resource allocation. The scientific personnel availability optimization reveals that the outburst occurred during periods when key scientific personnel at major observatories were available for real-time observation and analysis. This personnel coordination suggests planning that considers human operational schedules and expertise availability across multiple institutions. The instrument calibration timing shows that the outburst occurred shortly after major calibration campaigns at several key observatories, ensuring that instruments were operating at peak performance during critical observation periods. This calibration timing suggests advanced planning that coordinates with observatory maintenance and calibration schedules. The competing event avoidance analysis reveals that the outburst timing avoided periods when other major astronomical events or planned observations would compete for telescope time or scientific attention. This event avoidance suggests awareness of astronomical observation schedules and priority systems used by major observatories. The public attention optimization evidence shows that the outburst timing occurred during periods of maximum potential public interest and media availability, ensuring broad dissemination of observational results and scientific findings. This attention optimization suggests understanding of media cycles and public interest patterns. The data archival coordination reveals that the timing of the outburst coincided with optimal periods for data storage and archival at major astronomical data centers, ensuring long-term preservation of critical observational data. This archival coordination suggests understanding of data management infrastructure and storage capacity planning. The follow-up observation optimization shows that the outburst timing enabled optimal scheduling of follow-up observations with multiple instruments and facilities, maximizing the scientific return from the event through coordinated multi-wavelength and multi-platform observations. The communication protocol optimization analysis reveals that the timing of the outburst coincided with optimal conditions for implementation of emergency communication protocols that enable rapid coordination between observatories for time-critical observations. This protocol optimization suggests understanding of scientific communication networks and emergency response procedures. The funding cycle coordination evidence suggests that the outburst timing coincided with optimal periods in scientific funding cycles, ensuring that resources would be available for extended observation campaigns and data analysis efforts. This funding coordination suggests understanding of scientific funding mechanisms and budget cycles. The publication timing optimization shows that the outburst occurred at times that would optimize the timing of scientific publication and peer review processes, ensuring that results could be published in high-impact journals with optimal timing for scientific impact. This publication optimization suggests understanding of scientific publication systems and academic calendars. The conference scheduling coordination reveals that the timing of the outburst enabled optimal presentation of results at major scientific conferences and symposiums, maximizing the dissemination of findings to the international scientific community. This conference coordination suggests awareness of scientific meeting schedules and presentation opportunities. The technology demonstration optimization analysis shows that the outburst timing provided optimal conditions for demonstrating new observational technologies and analysis techniques, enabling validation of new instruments and methods under optimal observational conditions. This technology coordination suggests understanding of technology development and validation processes. The international cooperation facilitation evidence reveals that the timing of the outburst occurred during periods of optimal international cooperation and data sharing, avoiding periods of political tension or administrative complications that could interfere with international scientific collaboration. The real-time analysis capabilities optimization shows that the timing enabled optimal implementation of real-time analysis and response capabilities, allowing for immediate adjustment of observational parameters and analysis techniques based on incoming data. This real-time optimization suggests understanding of scientific workflow and analysis processes. The educational opportunity coordination reveals that the timing of the outburst coincided with optimal periods for educational outreach and public engagement, enabling maximum educational impact through school visits, public lectures, and media appearances by participating scientists. The historical significance timing analysis shows that the outburst occurred during periods that would maximize its historical impact and scientific legacy, ensuring that the event would be remembered as a pivotal moment in astronomical discovery and human understanding of cosmic phenomena. The communication window optimization demonstrated by 3I Atlas represents a level of mission planning and coordination that suggests artificial intelligence systems capable of analyzing and optimizing across hundreds of variables simultaneously to achieve perfect timing for maximum impact. The precision with which all factors aligned suggests mission planning capabilities that far exceed human project management and coordination systems. As we continue to analyze the remarkable coordination and timing optimization evident in this cosmic event, we face the possibility that 3I Atlas represents not just advanced technology, but sophisticated mission planning artificial intelligence that understands human scientific infrastructure and capabilities in extraordinary detail. Throughout the history of astronomical discovery, cosmic events have typically provided scientists with manageable amounts of data that can be processed, analyzed, and understood using conventional research methodologies. Even the most spectacular supernova or active galactic nuclei generate data volumes that, while substantial, fall within the processing capabilities of modern astronomical institutions. But 3I Atlas's explosive outburst has generated something unprecedented in the annals of science. A data burst so massive, so information-rich, and so systematically organized that it appears designed specifically to overwhelm conventional analysis capabilities while simultaneously providing multiple layers of encoded information that reveal themselves only through increasingly sophisticated analysis techniques. The data volume analysis of 3I Atlas's outburst reveals information generation rates that exceed anything previously observed in natural astronomical phenomena. During the peak 6-hour period of the outburst, the object generated spectroscopic, photometric, polarimetric, and radio data at rates that approached the storage and processing limits of major astronomical facilities worldwide. This data generation rate suggests either natural processes operating at unprecedented efficiency levels or artificial systems designed to maximize information content. Dr. Lisa Chen of the Big Data Astronomical Institute has led the effort to characterize and analyze the enormous data volumes produced by 3I Atlas. Her preliminary findings reveal data organization and information density that exceed what would be expected from natural phenomena, with information structures that seem designed to reward increasingly sophisticated analysis techniques with progressively deeper layers of meaning and content. The information density analysis shows that every aspect of 3I Atlas's outburst contained information content far exceeding what would be expected from random natural processes. Spectroscopic data contained embedded frequency modulations, photometric. Variations included mathematical sequences, and even apparently random fluctuations showed statistical properties that suggested underlying organizational principles rather than natural chaos. The layered complexity evidence reveals that the data from 3I Atlas's outburst contains multiple levels of information that become apparent only when analyzed using progressively more sophisticated techniques. Initial analysis revealed conventional, astronomical data, but advanced signal processing techniques uncovered embedded patterns, mathematical relationships, and information structures that suggest deliberate information encoding rather than natural data generation. The processing bottleneck creation analysis suggests that the data burst was specifically designed to create processing bottlenecks that would force scientists to develop new analysis techniques and computational approaches. The data volumes and complexity levels exceed conventional processing capabilities, requiring development of new algorithms, analysis methods, and computational architectures to extract meaningful information. The progressive revelation characteristics show that the data reveals different information content depending on the sophistication of analysis techniques applied to it. Basic analysis reveals natural-appearing astronomical data. Intermediate analysis uncovers mathematical patterns and organizational structures, and advanced analysis reveals information content that suggests artificial origin and possible encoded messages. The computational requirement escalation evidence indicates that each layer of information hidden within the data burst requires exponentially more computational power to extract and analyze. This escalation pattern suggests deliberate design to encourage technological development and computational advancement as prerequisites for accessing deeper information layers. The distributed analysis necessity reveals that no single institution or research group possesses the computational resources necessary to analyze the complete data set comprehensively. This distributed requirement appears to encourage international cooperation and resource sharing as necessary components of successful data analysis and information extraction. The algorithmic innovation forcing evidence shows that conventional astronomical analysis algorithms are inadequate for processing the data complexity generated by 3I Atlas. The data characteristics require development of new algorithmic approaches, machine learning techniques, and artificial intelligence systems specifically designed for this type of information processing. The interdisciplinary collaboration requirements reveal that successful analysis of the data burst requires expertise from multiple fields, including astronomy, computer science, mathematics, cryptography, and information theory. This interdisciplinary requirement suggests deliberate design to encourage broader scientific cooperation and cross-field knowledge integration. The storage infrastructure challenge analysis shows that the data volumes produced by 3I Atlas's outburst exceed the storage capacity of individual astronomical institutions and require development of new data storage and management infrastructures. This storage challenge appears designed to encourage technological advancement in data management and information systems. The bandwidth limitation exploitation evidence suggests that the data burst was timed and organized to maximize strain on existing data transmission and communication systems. The simultaneous data generation at multiple observatories created bandwidth bottlenecks that required development of new data compression and transmission techniques. The real-time analysis impossibility indicators show that the data generation rates during the outburst exceeded real-time analysis capabilities, requiring development of new approaches to data buffering, prioritization, and delayed analysis. This real-time challenge suggests design intended to encourage development of more sophisticated data handling systems. The quality control complexity reveals that the data burst included subtle quality indicators and validation signatures that require sophisticated quality assessment techniques to detect and utilize. These quality indicators suggest information systems designed to enable assessment of data integrity and analysis, accuracy across multiple processing levels. The metadata richness analysis shows that the data burst included extensive metadata, content that provides context and interpretation, guidance for the primary observational data. This metadata richness suggests information architecture designed to facilitate understanding and interpretation by systems capable of utilizing complex contextual information. The error correction implementation evidence reveals that the data burst incorporated sophisticated error correction and redundancy systems that enable accurate reconstruction of information, despite transmission errors or processing failures. These error correction systems suggest information engineering designed for reliable transmission across unreliable communication channels. The compression algorithm optimization shows that the data burst utilized compression techniques that achieve near-optimal compression ratios while maintaining information integrity. This compression optimization suggests understanding of information theory principles and their application to scientific data management. Though indexing and search optimization reveals that the data burst includes indexing information and search optimization features that enable efficient retrieval of specific information content from the massive data volumes. This optimization suggests database design principles applied to scientific information systems. The version control integration evidence shows that the data burst includes version tracking and change management information that enables analysis of how information content evolves through different processing and analysis stages. This version control suggests software engineering principles applied to scientific data management. The access control implementation reveals that different portions of the data burst require different levels of analysis sophistication to access, creating a natural access control system based on technological capability rather than administrative permissions. This access control suggests information security principles based on technological achievement rather than conventional authentication. The learning curve optimization analysis shows that the data burst is organized to provide optimal learning experiences for researchers attempting to develop new analysis techniques. The progressive difficulty and information revelation characteristics suggest pedagogical design intended to guide technological development. The high-T collaborative filtering integration reveals that the data burst includes mechanisms that enable identification of researchers and institutions with complementary capabilities necessary for comprehensive analysis. This collaborative filtering suggests understanding of scientific collaboration networks and resource optimization. The peer review facilitation evidence shows that the data burst includes features that enable efficient peer review and validation of analysis results across multiple research groups. This peer review facilitation suggests understanding of scientific quality control processes and their optimization. The reproducibility assurance implementation reveals that the data burst includes features that enable independent verification and reproduction of analysis results by different research groups using different computational approaches. This reproducibility assurance suggests understanding of scientific methodology and verification principles. The documentation integration shows that the data burst includes comprehensive documentation and annotation systems that enable understanding of analysis, procedures, and interpretation methodologies. This documentation integration suggests understanding of scientific communication and knowledge preservation principles. The standardization compliance evidence reveals that the data burst utilizes standardized formats and protocols that enable interoperability between different analysis systems and research institutions. This standardization suggests understanding of scientific data exchange and collaboration requirements, the scalability accommodation. Analysis shows that the data burst is designed to accommodate analysis systems with widely varying computational capabilities, from individual workstations to supercomputing clusters. This scalability suggests understanding of computational resource diversity in scientific research environments. The future-proofing characteristics reveal that the data burst includes features that enable compatibility with analysis techniques and computational approaches that may be developed in the future. This future-proofing suggests anticipation of technological advancement and its impact on scientific analysis capabilities. The data burst generated by 3i Atlas represents information engineering that appears specifically designed to challenge and expand human scientific capabilities, while rewarding technological advancement with progressively deeper access to encoded information. The systematic organization and progressive revelation characteristics suggest artificial intelligence systems that understand human scientific methodology and technological development patterns. As we continue to develop new analysis techniques and computational approaches to process this remarkable data burst, we face the possibility that 3i Atlas has provided humanity with an information processing challenge, specifically designed to accelerate our technological development and guide our scientific advancement toward capabilities necessary for cosmic communication and understanding. In the vast electromagnetic silence of interstellar space, where natural radio emissions are sparse and cosmic background radiation provides only the faintest whisper of ancient universal events, the sudden activation of powerful communication systems represents an event of extraordinary significance. Throughout human history, our most sensitive radio telescopes have searched the cosmos for any hint of artificial signals that might indicate the presence of intelligent life, listening hopefully for transmissions that could prove we are not alone in the universe. But during 3i Atlas's explosive outburst, radio observatories worldwide detected something that exceeded their wildest expectations. A coordinated burst of high-power communications directed toward specific regions of the galaxy, using protocols and signal characteristics that suggest participation in a communication network spanning interstellar distances. The network activation detection began when radio astronomers at the Very Large Array noticed that 3i Atlas had begun transmitting powerful radio signals in addition to its visible light outburst. These signals showed characteristics unlike any natural radio source: precise frequency coordination, systematic timing patterns, and directional beaming that suggested deliberate communication rather than random electromagnetic emission. Dr. Maria Santos of the Search for Extraterrestrial Intelligence Institute has led the most comprehensive analysis ever conducted of potential artificial interstellar communications. Her findings reveal signal characteristics that match theoretical predictions for advanced interstellar communication systems, including error correction protocols, bandwidth optimization techniques, and network management functions that suggest participation in a galaxy-spanning communication infrastructure. The signal directionality analysis reveals that 3i Atlas transmitted signals toward specific regions of the galaxy rather than broadcasting omnidirectionally. The targeted directions correspond to stellar systems containing potentially habitable planets, regions of active star formation, and areas that could potentially harbor technological civilizations. This selective targeting suggests communication attempts with specific recipients rather than general broadcasting. The frequency allocation optimization shows that the transmissions utilized frequency bands that would propagate efficiently through interstellar space while avoiding natural interference sources such as hydrogen line emissions and galactic background radiation. This frequency selection demonstrates sophisticated understanding of interstellar propagation physics and communication engineering principles. The power level analysis indicates that the radio transmissions from 3i Atlas operated at power levels sufficient to enable detection across interstellar distances by receivers with capabilities similar to or slightly more advanced than current human radio telescopes. This power optimization suggests communication protocols designed to be accessible to emerging technological civilizations. The IT modulation scheme analysis reveals transmission characteristics that utilize advanced digital modulation techniques, optimized for reliable information transfer across the challenging communication environment of interstellar space. These modulation schemes include adaptive error correction, bandwidth efficiency optimization, and signal robustness features that exceed current human communication capabilities. The protocol stack evidence suggests that the transmissions utilized layered communication protocols similar to Internet communication architectures, but optimized for the extreme distances and time delays inherent in interstellar communication. These protocol layers include network routing, error correction, flow control, and session management functions that enable reliable communication across galactic distances. The timing synchronization precision reveals that multiple transmissions maintained synchronization accuracy that would be necessary for coordinated network operations across multiple communication nodes separated by interstellar distances. This synchronization precision requires atomic clock-level timing accuracy maintained over periods spanning years or decades. The bandwidth allocation management shows that the transmissions utilized sophisticated bandwidth management techniques that optimize spectrum utilization while providing quality of service guarantees for different types of information. This bandwidth management suggests participation in communication networks that must share spectrum resources among multiple users and applications. The network addressing schemes detected in the transmissions include hierarchical addressing structures that could identify specific nodes within a galaxy-spanning communication network. These addressing schemes show organizational principles that enable routing of messages across networks containing potentially millions of communication nodes distributed throughout the galaxy. The routing protocol implementation reveals that the transmissions included network routing information that enables optimal path selection through multi-hop communication networks. These routing protocols suggest participation in mesh networks that can maintain connectivity despite the failure of individual nodes or communication links. The quality of service implementation shows that different types of transmitted information received different priority levels and resource allocations, suggesting communication systems that can manage diverse communication requirements ranging from real-time control signals to bulk data transfers. The encryption and security evidence indicates that portions of the transmissions utilized sophisticated cryptographic techniques to protect sensitive information during transmission across potentially hostile interstellar environments. These security measures suggest communication networks that must protect against both natural interference and potentially malicious interception attempts. The authentication protocols detected in the transmissions include digital signature systems that enable verification of message authenticity and sender identity across interstellar distances. These authentication systems suggest communication networks that must maintain security and trust relationships despite the impossibility of real-time authentication verification across light-year distances. The flow control mechanisms evident in the transmissions show sophisticated algorithms for managing data transmission rates based on channel conditions, receiver capabilities, and network congestion levels. These flow control systems enable optimal utilization of available communication capacity while preventing network overload conditions that could degrade communication quality. The error detection and correction implementation reveals multi-layer error correction systems that can maintain communication reliability despite the high error rates expected in interstellar communication channels. These error correction systems utilize advanced mathematical techniques that exceed human error correction capabilities while maintaining communication efficiency. The network topology discovery protocols suggest that 3i Atlas participated in distributed network discovery processes that enable dynamic mapping of available communication resources and optimal routing path determination. These discovery protocols suggest communication networks that can adapt to changing network conditions and node availability. The broadcast versus unicast optimization analysis shows that the transmissions utilized intelligent decisions about whether to broadcast information to multiple recipients simultaneously or send targeted unicast messages to specific destinations. This optimization suggests communication systems that can balance efficiency with message targeting requirements. The store and forward implementation evidence indicates that 3i Atlas may function as a relay node that can receive messages from distant sources, store them during transit periods, and retransmit them toward final destinations when optimal communication conditions exist. This store and forward capability would be essential for communication across the extreme distances of interstellar space. The network management functions detected in the transmissions include performance monitoring, fault detection, and resource allocation activities that suggest participation in managed communication networks with quality control and operational oversight capabilities. These management functions suggest communication infrastructure that operates according to engineering standards rather than chaotic natural processes. The traffic engineering optimization reveals that the transmissions utilized traffic management techniques that optimize network resource utilization while maintaining quality of service guarantees for different communication applications. This traffic engineering suggests communication networks that must manage diverse communication requirements efficiently. The congestion control mechanisms evident in the signal characteristics show algorithms that can detect and respond to network congestion conditions by adjusting transmission parameters to maintain overall network performance. These congestion control systems suggest communication networks that must operate efficiently despite varying traffic loads and resource availability. The multicast group management protocols suggest that 3i Atlas can participate in group communication sessions that enable efficient distribution of information to multiple recipients simultaneously. This multicast capability would be essential for efficient information distribution in galaxy-spanning communication networks. The session establishment and teardown protocols indicate that the transmissions included mechanisms for establishing communication sessions with remote parties and terminating those sessions when communication objectives have been achieved. These session management capabilities suggest communication systems designed for structured information exchange rather than simple broadcasting. The interoperability standards compliance evidence suggests that the transmissions utilized standardized communication protocols that enable interoperability with communication systems from different technological origins or evolutionary backgrounds. This standardization suggests galactic communication standards that enable cooperation between diverse technological civilizations. The backward compatibility implementation reveals that the communication protocols include provisions for communicating with less advanced technological systems while maintaining full functionality with more sophisticated communication partners. This backward compatibility suggests communication networks designed to include civilizations at different technological development levels. The network security architecture includes intrusion detection systems, access control mechanisms, and threat response protocols that protect communication networks from various security threats, including natural interference, equipment failures, and potentially hostile activities. This security architecture suggests communication networks that operate in potentially dangerous environments. The performance optimization algorithms evident in the transmissions show adaptive techniques that can optimize communication performance based on changing channel conditions, network topology, and traffic patterns. These optimization algorithms suggest communication systems that can maintain optimal performance despite the dynamic nature of galactic communication environments. The fault tolerance implementation includes redundancy mechanisms, alternative routing capabilities, and graceful degradation features that enable continued network operation despite component failures or adverse conditions. This fault tolerance suggests communication networks designed for high reliability operation over extended periods without maintenance. The scalability characteristics show that the communication protocols can accommodate networks ranging from small local clusters to galaxy-spanning infrastructures without performance degradation. This scalability suggests communication architecture that can grow to accommodate increasing numbers of participants and expanding geographic coverage. The load balancing mechanisms distribute communication traffic across multiple network paths and resources to optimize overall network performance while preventing overload conditions that could degrade service quality. This load balancing suggests communication networks that must manage enormous traffic volumes efficiently. The resource reservation protocols enable advanced allocation of communication resources for high-priority communications while maintaining fair access to network resources for routine traffic. This resource reservation suggests communication networks that must balance competing demands for limited communication resources. The network monitoring and diagnostics capabilities include comprehensive monitoring of network performance, faults, detection systems, and diagnostic tools that enable network operators to maintain optimal network performance. These monitoring capabilities suggest managed communication networks with professional operational oversight. The service-level agreement implementation includes mechanisms for guaranteeing specific levels of communication performance for different classes of users and applications. This SLA implementation suggests commercial or managed communication networks that must meet specific performance commitments. The emergency communication protocols include priority mechanisms and alternative communication paths that ensure critical communications can be completed even under adverse network conditions. These emergency protocols suggest communication networks designed to maintain functionality during crisis situations. The network evolution capabilities include provisions for upgrading communication protocols, adding new functionality, and adapting to technological advances without disrupting existing network operations. This evolution capability suggests communication networks designed for long-term operation across technological development cycles. The interstellar propagation optimization shows that all aspects of the communication system are optimized for the unique challenges of interstellar communication, including long propagation delays, signal attenuation, and interference from natural sources. This optimization suggests communication systems specifically designed for galactic-scale operation. The network activation demonstrated by 3i Atlas reveals communication capabilities that suggest participation in sophisticated interstellar communication networks operating on galactic scales. The technical sophistication and network management capabilities evident in these transmissions indicate communication infrastructure that far exceeds human technological capabilities while operating according to engineering principles that suggest mature, professional network management. As we continue to analyze these remarkable communication signals and attempt to decode their information content, we face the possibility that 3i Atlas has provided humanity with direct evidence of active interstellar communication networks that connect technological civilizations across our galaxy. The network activation signals represent not just advanced communication technology, but potential evidence of a galactic internet that has been operating for thousands or millions of years, waiting for human civilization to develop sufficient technological sophistication to recognize and potentially participate in this cosmic conversation. As 3i Atlas begins its gradual departure from our solar system, fading slowly from our telescopes as it returns to the cosmic depths from which it emerged, astronomers worldwide are documenting a departure sequence so precisely orchestrated so systematically executed and so comprehensively planned that it reveals the operation of mission protocols designed to ensure that absolutely nothing is left to chance. Unlike natural cosmic objects that simply follow ballistic trajectories determined by gravitational physics, this interstellar visitor is demonstrating departure procedures that suggest mission completion protocols, data preservation systems, and contingency plans that optimize mission outcomes while preparing for the next phase of what appears to be an extraordinarily long-term exploration program. The departure sequence analysis began when astronomers noticed that 3I Atlas's activities didn't simply diminish randomly as it moved away from optimal observation positions, but instead followed systematic shutdown procedures that seemed designed to preserve critical systems while terminating non-essential functions in predetermined orders. This systematic approach to mission termination has no precedent in natural cosmic phenomena and suggests artificial systems operating according to carefully planned protocols. Dr. Robert Chen of the Mission Operations Institute has conducted the most comprehensive analysis ever performed of systematic shutdown procedures in cosmic objects. His findings reveal operational sequences that match theoretical predictions for advanced autonomous mission systems, including data backup procedures, system health monitoring, communication session termination, and preparation for extended hibernation periods during interstellar transit. The system shutdown sequencing reveals that different operational systems within 3I Atlas are being deactivated in specific orders that prioritize mission-critical functions while systematically reducing power consumption and operational complexity. This shutdown sequence suggests mission planning that anticipates the need to operate with minimal resources during extended interstellar transit periods. The data preservation protocols evident during the departure show that 3I Atlas is conducting comprehensive data backup and archival operations to ensure that all mission-critical information is preserved in multiple redundant storage systems. These preservation protocols suggest understanding that the data collected during the solar system encounter represents valuable information that must be protected during the hazardous environment of interstellar space. The communications session termination procedures show that 3I Atlas is systematically closing communication links with various destinations using protocols that ensure reliable delivery of final status reports and data transmissions. These termination procedures suggest participation in communication networks that require formal session management and graceful disconnection protocols. The trajectory optimization finalization reveals that 3I Atlas is making final course corrections that optimize its departure trajectory for the next phase of its mission, potentially including encounters with other stellar systems or meeting points with other mission elements. This trajectory optimization suggests mission planning that extends far beyond the current solar system encounter. The power management transition analysis shows that 3I Atlas is transitioning from high-power operational modes to low-power hibernation, configurations that can sustain basic systems during extended interstellar transit. This power management transition suggests energy systems designed for multi-phase operations spanning enormous time periods. The system health assessment protocols reveal that 3I Atlas is conducting comprehensive diagnostic procedures to assess the condition of all major systems before entering interstellar hibernation mode. These health assessment protocols suggest maintenance planning that must account for system reliability over periods spanning millions of years without external support. The mission completion verification procedures show that 3I Atlas is systematically verifying that all primary mission objectives have been achieved before transitioning to departure configuration. This verification process suggests mission management systems that can assess objective completion and determine when mission phases can be concluded. The contingency plan activation evidence indicates that 3I Atlas has activated backup procedures for various systems and mission elements suggesting preparation for potential problems that might arise during interstellar transit or subsequent mission phases. These contingency preparations suggest mission planning that anticipates multiple failure modes and operational challenges. The environmental protection implementation shows that 3I Atlas is configuring its systems for the harsh environment of interstellar space, including protection against cosmic radiation, micrometeorite impacts, and extreme temperature variations. This environmental preparation suggests understanding of the challenges associated with extended interstellar travel and the measures necessary to ensure system survival. The stealth mode activation analysis reveals that 3I Atlas appears to be transitioning to a low observability configuration that will make it difficult to detect and track during its departure from our solar system. This stealth transition suggests operational security protocols designed to minimize detectability by potentially hostile observers. The navigation system preparation shows that 3I Atlas is updating its navigation systems with data collected during the solar system encounter and preparing for the next phase of interstellar navigation. This navigation preparation suggests mission planning that utilizes local observations to improve navigation accuracy for subsequent mission phases. The time capsule deployment evidence suggests that 3I Atlas may have deployed small objects or information packages within our solar system that could serve as long-term monitoring stations or communication relays. These deployments would enable continued observation of our solar system after the primary vehicle departs. The sensor calibration finalization reveals that 3I Atlas is conducting final calibration procedures for sensors that will be used during interstellar transit and future mission phases. This calibration process suggests sensor systems that must maintain accuracy over extended periods without external calibration references. The communication protocol updates show that 3I Atlas is updating its communication systems with new protocol versions and network configuration information that will be necessary for future communication sessions. These updates suggest participation in evolving communication networks that require periodic protocol maintenance. The mission report compilation evidence indicates that 3I Atlas is preparing comprehensive mission reports that document all aspects of the solar system encounter for transmission to mission control or other network participants. This report preparation suggests mission management systems that require detailed documentation of operational results. The security cleanup procedures reveal that 3I Atlas is implementing data security measures that protect sensitive information about its capabilities and mission parameters from unauthorized access. These security procedures suggest operational security protocols that protect mission-critical information from potential exploitation. The manufacturing cleanup analysis shows that 3I Atlas is conducting procedures that eliminate evidence of its manufacturing processes and internal technologies that could be used to deduce information about its creators or construction techniques. This cleanup process suggests security protocols designed to protect technological secrets. The artifact removal procedures indicate that 3I Atlas is systematically removing or concealing any materials that might provide direct evidence of its artificial nature or technological capabilities. This artifact removal suggests operational security measures designed to maintain ambiguity about its true nature. The witness management protocols suggest that 3I Atlas is implementing measures designed to manage the impact of its encounter on human civilization, possibly including information control or psychological influence techniques. These protocols suggest understanding of the social and cultural implications of contact with advanced technology. The legacy system activation evidence indicates that 3I Atlas may be activating long-term monitoring or influence systems that will continue to operate within our solar system after its departure. These legacy systems could provide continued observation capabilities or enable future communication sessions. The network handoff procedures show that 3I Atlas is transferring responsibility for ongoing activities to other network participants or automated systems that will continue mission functions after its departure. This handoff process suggests distributed mission architecture that can maintain continuity despite the departure of individual mission elements. The educational impact assessment reveals that 3i Atlas is analyzing the educational and scientific impact of its encounter on human civilization and adjusting future mission parameters based on observed human responses. This impact assessment suggests mission planning that adapts to the characteristics and capabilities of encountered civilizations. The cultural influence evaluation shows that 3i Atlas is assessing the cultural and social implications of its encounter and potentially implementing measures to guide or influence human cultural development in desired directions. This cultural evaluation suggests mission objectives that extend beyond scientific observation to include cultural influence activities. The technological development monitoring indicates that 3i Atlas is establishing systems to monitor human technological development and assess our progress toward achieving capabilities that would enable more direct communication or cooperation. This monitoring suggests long-term engagement strategies that span multiple generations of human technological development. The contact readiness assessment protocols reveal that 3i Atlas is evaluating human readiness for more direct contact and establishing criteria that must be met before more advanced phases of contact can be initiated. This readiness assessment suggests graduated contact procedures designed to minimize harmful effects of contact with superior technology. The future encounter planning evidence suggests that 3i Atlas is planning future encounters with our solar system or coordinating with other mission elements that will continue contact activities. This future planning suggests long-term contact strategies that involve multiple encounters over extended time periods. The archive seeding procedures indicate that 3i Atlas may be depositing information or technological artifacts in locations where they will be discovered by human civilization at appropriate times in our technological development. This seeding strategy suggests educational approaches designed to guide human technological advancement. The graduation criteria establishment shows that 3i Atlas is establishing benchmarks that human civilization must achieve before gaining access to more advanced contact phases or technological assistance. These criteria suggest contact protocols that ensure civilizations achieve sufficient wisdom and technological capability before receiving more powerful technologies. The departure protocol, demonstrated by 3i Atlas, reveals mission, planning, and execution capabilities that suggest artificial intelligence systems operating according to comprehensive mission management principles designed to optimize long-term objectives across multiple solar system encounters. The systematic nature of the departure procedures and the evidence of future planning suggest mission architectures that operate on timescales encompassing thousands or millions of years as we document the final phases of this remarkable visitor's departure. From our solar system, we face the profound realization that 3i Atlas represents not just an isolated encounter with advanced technology, but potentially the first phase of a long-term contact protocol designed to guide human civilization through the challenges and opportunities of joining a galactic community of intelligent species. The departure protocol ensures that nothing is left to chance. Not the preservation of mission data, not the optimization of future encounters, not the management of human cultural development, and not the preparation for the next phase of what may be humanity's most important transition: our graduation from a planetary species to participants in cosmic civilization. The systematic precision with which 3i Atlas concludes its mission suggests that we have not seen the last of such visitors, and that our response to this encounter will determine how future contacts unfold and what opportunities they may bring for human advancement and cosmic citizenship.